You finish editing a quick video, you hit publish on your story, and there it is, live on your profile. You refresh the page, and the video is still right there. As far as you're concerned, the action is complete. But if a friend sitting in another country pulls up your exact same profile at that exact same second, they won't see your new video. They might look at a loading screen, or they might just see your old content. This map shows how servers communicate. If engineers wanted your friend to see your video at the exact millisecond you do, they would have to enforce global consistency. That means when one server receives your video, it sends out verification pings to every single other server on Earth. It freezes all network traffic until every node confirms it has the update. It is incredibly slow and extremely expensive. Distributed systems bypass that bottleneck using client-centric consistency. Instead of forcing the entire global network to perfectly synchronize every millisecond, the system creates a localized bubble around you. It guarantees that your individual experience with the app is flawless and sequential, even if the rest of the world hasn't caught up yet. Modern applications prioritize keeping your personal digital timeline intact over maintaining absolute instantaneous truth across thousands of global servers. To maintain this localized bubble, the system has to enforce strict rules for how your device handles data. It starts with how information is retrieved. This graph shows a user's view of a metric over time. Under a rule called monotonic read consistency, once you read a piece of data, like seeing your post has 120 likes, you will never be shown an older version of that data in the future. The metric can stay at 120 or go up to 150, but it never dips backward down to 90. A stalled like counter is a minor annoyance, but a counter that seemingly deletes 30 likes on a page refresh breaks your trust in the app. The system actively intercepts and rejects incoming data packets that carry timestamps older than what you've already seen. This diagram maps a similar rule applied to the data you input, known as monotonic write consistency. This ensures that any sequence of actions you submit to the server is executed strictly in the order you sent them. If you update your profile bio to say hello, and a few seconds later update it to hello world, the server processes hello first and hello world second. It will never accidentally apply the shorter, earlier edit last. Both of these monotonic rules serve a single purpose. They ensure your personal timeline of interactions only ever moves forward, preventing strange temporal glitches on your screen. This diagram maps out a third rule: read your writes consistency. When you push new data up to the server, the system instantly reflects that exact update back to your screen, bypassing the slower process of updating the entire global network. This is why when you hit send on a direct message, it pops up in your chat log immediately. You get instant visual confirmation that your action was successful. This chart illustrates the fourth rule: write follows read consistency. Any new action you take is structurally anchored to the most recent version of the data you just viewed. If you pull up version 3 of the document and make an edit, your new save file specifically locks on to version 3, rather than accidentally overwriting version 2. If you are scrolling through a social media feed and reply to a specific post, your comment is logically chained to the exact state of the post you are reading at that moment. You see all 4 of these rules operating simultaneously in an app like WhatsApp. You open a chat and see messages in the correct order without old texts popping up. That's monotonic read. You fire off 3 quick texts and they queue up chronologically. That's monotonic write. Your texts appear on your screen the instant you send them. Read your writes. And when you swipe to quote a specific message, your reply attaches perfectly to that text. Write follows read. With these 4 pillars standing together, your digital reality feels entirely cohesive. You remain oblivious to the fact that servers halfway across the globe are still racing to copy and paste your conversation. This diagram shows a balance scale representing the deliberate compromise of a client-centric architecture. It forces engineers to weigh localized perfection for the user against managing a highly complex underlying system. Prioritizing the client side is what makes real-time applications practical and fast. It allows a platform to handle billions of simultaneous users without collapsing under the weight of constant server verification. But by sacrificing global consistency, the system guarantees that different users across the world will temporarily see conflicting versions of the same data until the servers finally sync up. If you need to memorize these models for an exam, just remember the acronym MR, MW, RYW, WFR. That stands for monotonic read, monotonic write, read your writes, and write follows read. In the architecture of modern digital life, absolute global truth is secondary. The highest priority is ensuring your individual,